Hi everyone, this is the final part of the practical 2 on discipline on the subject simulation of processes in avionics. At the previous class and previous video we talked about how to decompose the signal using the system of basis functions. We use this cosine of pi times t squared signal as an example and a set of 5 power functions as a system of basis functions that we wanted to decompose our signal onto. So the interval was from 0 to 1, and we've obtained the vector of coefficients x's to represent the signal, to decompose the signal in form of by these basis functions as in form of polynomial. So the recovery of the signal from its basis functions can be generated as this polynomial, where we just sum up all these basis functions, but prior to summing them up we multiply every basis function by a corresponding coefficient x capital from k. K stands for the number of the basis function. K runs from 0 to n. In our case it runs from 0 to 4. We've got 5 basis functions. So we just need to generate a system which would simulate the operation of this simple equation. Let's switch to the Matlab and let's see. But first we start simulation of this decomposition again and take a look at what we've got here. So we've got the coefficients, decomposition coefficients, which are illustrated here. They've been stored in the working space, Matlab's workspace. We can check them out. We can output them here by just typing sim out. So we've got these coefficients and their whole previous history of how do they develop. Actually, we can plot these coefficients, plot all columns, and we've got the whole history of how every coefficient develops in time. So, but we need only final values of this every coefficient. Final value. We can disregard this whole history and we need to pick just these final values. Let's go to the recovery subsystem. To recover the signal we need to pick these coefficients from the workspace of the Matlab. So to pick this we just go to the subsystem, to this source which can be found on the Simulinks library under the sinks and sources. This is the source from workspace. This is the component letting you to input data from the workspace. So, and we need to tune it up. So the data will come as a structure. The data will come with a structure. The first column will be disregarded. It represents the timestamp. The second column, these brackets represent actually the matrix of the structure. The second element, sim out, and we pick the sim out, the 55th row, and all the columns in this particular row, and we pick all the columns. So the number of this row is 55th, and we pick all these columns, which are 5. So this will be our input data. These are our input data. So now actually these data are illustrated here. If we compare, we see that these are the same coefficients. So we pick this last 5 columns of this particular row, of 55th row. So what happens next? We've got this system of basis functions outputted by the same previously known and previously created subsystem of basis functions. Now, to generate this polynomial, instead of doing individual multiplications of every coefficient by corresponding basis function and summing them up, we use the matrix product, which is called the dot product. Actually, this dot product allows us to multiply the corresponding values of x's, the coefficients of decomposition, times corresponding function, times the corresponding function, and sum them up. So at the output of dot product, we actually are getting this polynomial. We're actually getting this polynomial. We multiply the first coefficient times the first basis function plus second coefficient times the second basis function, and so forth. So at the output we get all this recovered signal recovered from the system of basis functions. To compare the recovered signal x sub a with the actual signal, again we introduce this subsystem which represented the actual signal. Now we run the simulation and take a look at the scope. We auto-scale it a little bit, and we see that this gray line or brown line, or actually yellow line, represent the actual signal. The purple line represents the recovered signal, the signal recovered from the basis functions by summing up these basis functions. We see that these functions are pretty close, but there's no perfect fitness of the recovered signal to the actual signal. So there is some error. We can play with this actually. We see what happens if we don't take the final value of the coefficient and we take some value from previous history. Say we go 5 time samples back and we pick the 50th element from the history. And what happens to the representation? We see that the error increases, especially at the end of the time interval. So we moved our coefficient somewhere here. So before we've got the almost perfect fitness of the recovered signal and the actual signal, but at the end of the interval there is an error which is increasing. So if we move even further into the history, like let's pick the 40th element, and run simulation again. We auto-scale. We see that error increases starting from that particular moment. Somewhere around the 40th element, the error starts growing. So it's happening as we move even further into the history. 20th element. We pick the 20th element. And we run the simulation again. We see that error just keeps increasing, because our polynomial does not represent the whole interval. It represents only the part of the interval in this integration. So instead of picking x which corresponds to the end of the interval, we picked some x's from the transient process. So we put it back. We put the 55th element here. We run the simulation. We look at the scope, and we see that there's almost, well, there's a good fitness of recovered signal and the actual signal. So this is it for this video, and at the next class and next video we'll talk a little bit about why do we need these representations. Why do we need represent or expand the signal by by other signals or other functions? Why do we need this? So until next time, take care guys, and bye.